All right, let's dive into a force that's completely invisible but powerful enough to bend beams of electrons and literally drive the motors that power our world. We are talking about the magnetic force. And look, if you're gearing up for your board exams, you absolutely have to master this topic. By the end of this explainer, I promise you'll have it down cold.
So let's kick things off with a really big question. We all know magnetic fields can do things like attract paper clips or repel other magnets, but can they actually reach out and influence a single tiny moving charge, like an electron? Can a magnetic field physically force it to change its path? Let's find out.
The answer is a huge yes, and you can actually see the proof in this classic experiment. Now, in an old school TV, one of those big cathode ray tube ones, the picture is made by shooting a beam of electrons at the screen. Watch what happens when you bring a magnet close by. The picture gets all warped and distorted. That's direct visual proof that the magnetic field is literally bending that beam of moving electrons.
Okay, so we've seen the effect in action. Now it's time to get into the nitty-gritty physics. In this first part, we're going to move from just watching what happens to actually calculating the force on a moving charge. So what is this magnetic force? Well, the definition itself holds the single most important rule you need to remember. The force is exerted by a magnetic field on a moving electric charge. I'm going to say that again, a moving charge. If you have a charge just sitting still in a magnetic field, it feels absolutely nothing. Zero, nada. Motion is the key ingredient here. Now for the formula that you absolutely must have memorized for your exams. This is the simple case. When a charge, which we call Q, is moving with a velocity v, and it's moving perfectly perpendicular to a magnetic field B, the force is just the product of all three. F equals Q times V times B. Super straightforward. This tells you that the force gets stronger if the charge is bigger, if it's moving faster, or if the magnetic field is more intense. But, things aren't always perfect. What happens when the charge isn't moving perfectly perpendicular to the field? Well, for any angle, we just tweak the formula a little bit. The general formula, and the one you're going to use most of the time, is F equals QVB sine theta, where theta is the angle between the velocity and the magnetic field. That little sine theta term is what makes the formula work for any situation you can throw at it. Okay, so using that new formula, let's pause for a second and think. What happens to the force if the charge moves perfectly parallel to the field lines? Think about what the angle theta would be in that case. The answer is 0. A big, fat 0. If the charge is moving parallel to the field, the angle theta is 0 degrees. And as you probably know, the sine of 0 is just 0. So the whole right side of the equation becomes 0, meaning the force is 0. The charge just sails right on through, completely unaffected. Now, this leads to one of the coolest and most important consequences of the magnetic force. It makes charged particles move in circles. But why? Well, think about it. The force is always perpendicular to the direction the charge is moving. It's not pushing it forward to speed it up or backward to slow it down. It's only ever pushing it sideways. And what happens when you have a constant sideways force? You get circular motion. It's the very definition of a centripetal force. And because the magnetic force is acting as a centripetal force, we can actually derive some really important properties of this circular path. Now, this is a super common exam question, so pay close attention. Step 1. We just equate the two forces. The magnetic force, QVB, is the centripetal force, mv squared over r. So let's just set them equal to each other. Step 2. Let's solve for the radius r. With a little bit of simple algebra, we just rearrange the equation, and we find that the radius of the circle is mv divided by qb. Step 3. Now let's solve for the time period t, which is how long it takes to go around once. Time is distance over speed, right? So that's the circumference, 2 pi r, divided by the velocity v. Now we just plug in that expression for r that we just found, and look at that, the v terms cancel out. We're left with a nice, clean expression for the time period. T equals 2 pi m divided by qb. So far, we figured out the magnitude of the force, how strong it is. But force is a vector, which means it also has a direction. We need to know which way that charge is actually going to get pushed. To do that, we use a simple but really powerful tool. And that tool is the right-hand rule. Come on, let's do this together right now. Take your right hand. First, point your forefinger, your index finger, in the direction of the charge's velocity, v. Got it? Okay, now point your middle finger in the direction of the magnetic field B. The direction your thumb is now pointing, that's the direction of the force, F.
So it's velocity, field, force. Practice that a few times. It's super useful. But wait, here's the common trap that gets a lot of students. The right-hand rule we just did, that's for positive charges. So what do you do if you have a negative charge, like an electron? It's actually really simple. You do the exact same thing with your right hand, find the direction your thumb points, and then the real force is in the exact opposite direction. You just flip it 180 degrees. Don't forget that step. Okay, we've totally nailed the force on a single lonely charge. Now let's scale things up. What happens when we don't have one charge, but billions and billions of them all moving together inside a wire? Let's talk about the force on a current-carrying wire. It's really simple when you think about it. What is an electric current? It's just a whole bunch of charges moving in the same direction. It's a massive collection of moving charges. So if every single one of those individual charges is feeling a little magnetic push, it makes sense that the wire that's holding them all is going to feel the grand total of all those tiny pushes. It's going to feel one single large-scale force. And we can derive the formula for this force right from our single charge equation. Let's just walk through the logic. We start with what we know. F equals QVB, where Q is the total charge in some length L of the wire. Next, what's velocity? It's just distance over time, so we can say V equals L divided by T. Let's substitute that in. Our formula now looks like F equals Q times L over T times B. Now watch this. Let's just rearrange the terms a little bit to group Q and T together. We get F equals Q over T times L times B. And what is Q over T? The amount of charge that flows per second? That's the definition of electric current, I. So we're left with our final beautiful formula, F equals ILB. And you guessed it, just like with the single charge, there's a general version for when the wire is at an angle to the field. It's F equals ILB sine theta. And once again, if the wire is parallel to the field, theta is 0, sine of theta is 0, and the force on the wire is 0. So the formula is fantastic for getting the right answer on an exam. But this is physics. We want to understand why. Why does this force even happen? The right-hand rule tells us which way it's going to move, but it doesn't really explain the deep reason for that push. This is the aha moment. Here's what's really going on. First, remember that a wire with current flowing through it generates its own circular magnetic field all around it. Second, we take that wire and we place it inside another magnetic field, like the one from this horseshoe magnet. So now we have two fields interacting. On one side of the wire, the fields are pointing in the same direction, so they add up, they reinforce each other, and you get a strong, concentrated magnetic field. But on the other side of the wire, the fields are pointing in opposite directions, so they partially cancel each other out, creating a weak magnetic field. And just like a ball rolling downhill, things in physics like to move from high pressure to low pressure. The wire gets physically pushed from that stronger field region toward the weaker one. That physical push is the magnetic force. All right, we've covered a lot of ground. Let's wrap this up with a quick-fire recap that puts everything side by side. This is perfect for your final revision before the exam. Let's just quickly compare the two main ideas here. The physics behind them is really the same, but the formulas are just scaled differently. For a single charge, the force depends on its individual charge Q and its velocity V. For a wire, we're not looking at one charge, we're looking at the collective flow, which we call current, I, over a certain length, L. But notice how the structure of the formula, something times B times sine theta, stays exactly the same. And if there's one single idea that you take away from this entire explainer, please let it be this. Because that magnetic force is always perpendicular to the direction of motion, it can never do work on the charge. It can't make it go faster, it can't make it go slower. A magnetic field does not change the speed of a charge. It only and always changes its direction.